Important project, which helps me a lot to understand elliptic curves, is 524. So let me go through some of that, because here you actually get to make some of these curves and see them go, and it makes it a lot easier to understand them. And all we need for this is a command prompt and a machine with Python, like the Mac, for example. You can also use your Linux. You can probably do it on Windows too. So first we're going to find the points on the curve. We need to install this library. So I'll just do that here. In fact, let's go to 141 and do it here. Right. So I download this library and then install it with Python. So I have elliptic curve capability in my Python here. All right. Now, here's a simple curve with a modulus of 5, so it's going to be ridiculously small, like the ones we did with RSA, and A and B are just 1 and 2. So if you have a case of x equal -1, then -1 cubed is -1. This is -1 plus 2, so this is 0. So the answer is y equals 0. -1, 0 is an answer. And you could also write that as 4, 0, modulus 5, because -1, remember in modular arithmetic, -1 modular 5 is 4, 1 below 5. So this is the point, 4, 0, it's on the curve. And you've got to find out how many points are on the curve. So there's an on-curve function that will do this. So let me run Python. And let's find out, whoops, got to spell it better than that. Let's find out how many points are on this curve. So here's the curve. There's the first point. And now I'm just going to say if on the curve, print it's on the curve, else print it's not on the curve. So, on curve is not defined. I've somehow missed the import. Yep, I got to do this import or nothing's going to work. All right. So now I should be able to do this. All right, and so 4, 0 is on the curve. That's just use the on-curve function. If it's on curve, print it's on the curve. Otherwise, it's not on the curve. So now we can find all the points on the curve. These parameters have already been defined. Now all I have to try is all values for x and all values for y, and check and see if it's on the curve, and print the ones that are on the curve. So there's only 3 points on the curve, 4, 0, 1, 2, and 1, 3. And the point at infinity is also on the curve, but it doesn't show up in this test. So there are a total of 4 points on the curve. And you would have known that because the modulus is 5. And typically, it's not always exactly equal to the modulus, but it's close to that. So let's change b to 1. I can just set b equals 1. Before, I think we were using a b of 2. And now I can find the points on the curve again. With the same code, I can try all the code there. If I change the parameter, now there's more points on the curve. See 0, 1, 0, 4, 2, 1, and so on. So 2, 4, 6, 8 points on the curve, plus 1 more for the point at infinity. A total of 9 points are on this curve. All right, and like I say, it's simple. It's probably best to just think of them as random numbers. And there's some way to combine them to get to a number that graph of figuring out how to connect 2 points and stuff is not terribly helpful. So there's a couple of flags to find, how many points are on a couple of curves. And now we can try scalar multiplication. There is a function called scalar multiplication that will take a constant k and multiply this point, px and py, by k, for this curve, a, b, and p. Remember, a, b, and p are the parameters for the curve. A and b are used for the y equals x cubed plus ax plus y plus b, and p is the modulus. So if I have a1, 1, and 5, which I think is what I've got right now, a is 1, it's not listening to me, a is 1, b is 1, and p is 5, all right? So we saw these points are on that curve. So now we can try multiplying 0, 1. So I've already got that. So if I start with x and y equal to 1, and then I just calculate the first 15 multiplications. That's what this will do. So I'm just going to try multiplying by numbers from 0 up to 14. That's what this will do, and print them all out. So you multiply it by 0, you get the point at infinity, which it writes down as none, none. You multiply it by 1, you get 0, 1. Double it, you get all these other numbers. And notice by the time you multiply it by 9, you're back to none, none again. And it just repeats from that point on. So this, and we already know how many points there are in this curve. There are 8. 2, 4, 6, 8. So this is a generator of the curve. This 0, 1, if you multiply by constants, will create every number on the curve. So that's a good property and something we need for cryptography. So now we can do all the multiples of all 8 points on the curve this way. Down here, now what this is going to do is here are all the points for p, x, p, y, n. I've just listed all the 8 points here in brackets. It'll try them all and then do the 10 multiplications of each of them. So now we get a list of results. So here's the first one we saw before. 0, 1 will repeat when you're only on the 9th one, so it's a generator of the whole curve. You have 0 and all 8. The 0, 4 is also a generator. The none doesn't come back until the end, but 2, 1 does not generate them. 2, 1 just goes through a loop of 3. And this is why, I said before, this is how that malicious attack worked. If you can feed them a point which has a property like this, where it just goes around a little loop, then you can reverse the discrete logarithm problem. This is why you don't want this to happen. Then you even don't really have a lot of bits in your key. You think you do, but you might as well only have a few bits because it's going around a short little loop. And see, this one here is also not a generator. This one is a generator. You know, some points are generators of the curve. Some leave you in little loops. All right. And so, let's take a look at Diffie-Hellman. I hate this Unicode nonsense. Anyway, all right, so A is 0. Here's a bigger curve. This is the actual Sec 256 K1 curve, but with a very small modulus. So P equals 17, and we're going to use that curve. All right. Right, they're using that equation, but not the large value. All right, so let's do it one step at a time. First, we're going to find the points on the curve. That's what this much will do. So it defines the curve with A, B, and P, and then it creates an array of objects P, and now for Px over all possible values and Py over all possible values, it's going to see if they're on the curve and add them to this list, and then it's going to print out the list. So there are 17 points on the curve, and there they are, 1, 5, 1, 12, and so on, these effectively random points. Now, we can try multiplying them. So we're going to see which ones are generators, and I think we're just going to prove that 15, 4 is a generator. Here's 15, 4. It's just one of the points on the curve, and it is a generator, which you can prove here. This is going to multiply it by all the numbers from 0 to 19 and print out the results. And so you have none, none, and then a whole lot of points, and here's the none, none up here at 18. And we know there are 17 points on the curve plus 1. So it is a generator. It doesn't repeat until you get down to here. All right, and so now we can do key agreement. Here's the same stuff we've done before for RSA. So these people each choose first they choose a curve and a generator. So they're going to use this curve for 17 and a generator. Now they choose a random secret key, which is 4 here and 7 here. And of course, with these small numbers, nothing is going to be secure, but you see how it works. Now they calculate the public key by taking 4 times the generator, which gets you to here. And Megan calculates her public key the same way. Then they exchange them, and then you multiply your private key times the other person's public key to agree on a shared secret, which is 112, and the other person will get the same value, 112. All right. So that's how it works. And so here's the discrete logarithm problem, where you try to find the alpha such that A is alpha times G. And that is very difficult. And all right. And you'll be able to do it just by brute force for these small values. All right, and then we've got more things here with the signature algorithm and such, but I don't think I'll continue going through it. You can try that one and see how you like it. But it's good to play with it a little bit. I understood elliptic curves a lot better after doing these simple examples. All right.